Close your eyes and take a slow, deep breath. Tonight, we're going on a gentle journey to explore one of the universe's most fascinating mysteries, black holes. These aren't the monsters of science fiction, but natural phenomena that emerge from the quiet mathematics of gravity and spacetime. As you relax into this exploration, let your mind drift through the cosmos, where massive stars end their lives in transformation rather than destruction, where space and time weave together in ways that challenge our everyday understanding. Black holes are places of profound stillness, where gravity has shaped reality into something beautifully strange. Over the next hours, we'll trace their entire existence, from birth in collapsing stellar cores, through their long lives at the centers of galaxies, to their eventual return to the quantum realm through a process so gradual it spans longer than the current age of the universe. There's no need to grasp every detail. Simply let the ideas wash over you like gentle waves, carrying you toward rest. The universe is patient, and so are we. Let us begin at the end of a star's life, where black holes are born not from violence but from inevitability. When a star many times more massive than our sun exhausts the nuclear fuel in its core, something profound happens. The forces that have supported it for millions of years can no longer resist gravity's patient pull. The star has spent its life in balance, with the outward pressure from nuclear fusion holding back the inward crush of its own mass. For a star 20 or 30 times the sun's mass, this balance lasts only a few million years, a brief moment in cosmic time. As fusion slows and eventually stops, gravity finally wins this ancient contest. The core begins to collapse, not explosively but almost gracefully, falling inward under its own weight. In less than a second, material that once occupied a region larger than Earth compresses to the size of a city, then smaller still. The outer layers of the star may rebound in what we call a supernova, scattering elements into space, but the core continues its inward journey. This is not destruction, it is transformation, a change of state as natural as water freezing into ice, though far more profound. Nothing in the known laws of physics can halt this collapse once it begins, and so the core continues to shrink, passing through densities that would seem impossible, approaching a point where our usual understanding of space and time begins to dissolve. This moment of transformation is where our story truly begins. As the stellar core collapses past a critical threshold, something remarkable occurs in the geometry of spacetime itself. An event horizon forms. This boundary is not made of anything material. You could not touch it or see it directly. It is instead a consequence of how gravity warps the very fabric of space and time. Think of it as a point of no return written into the structure of reality itself. The size of this boundary depends entirely on how much mass has collapsed. More mass creates a larger horizon. For a black hole containing 10 times the sun's mass, this boundary sits approximately 30 kilometers from the center. For the supermassive black holes at the hearts of galaxies, containing millions or billions of solar masses, the event horizon can be millions of kilometers across. What makes this boundary so significant is its relationship with light. We know that nothing can travel faster than light, and light itself always moves at the same speed through empty space. But near this boundary, space-time is curved so severely that light, despite moving at its constant speed, cannot escape to the outside universe. Any photon crossing this threshold, regardless of which direction it attempts to travel, will find all its possible paths lead inward. This is not because something is pulling the light back, but because the geometry of spacetime itself has curved in such a way that outward no longer exists as a direction from inside the horizon. Outside this boundary, you could still orbit or escape if you had sufficient velocity. But once across, return becomes not just difficult but geometrically impossible. This is the defining characteristic of a black hole, a region where the structure of spacetime has permanently closed off access to the external universe. The term event horizon is beautifully descriptive when you consider its meaning carefully. An event is anything that happens at a specific place and time. A horizon, in our everyday experience, is the limit of what we can see, the boundary of the observable world. The event horizon of a black hole is precisely this, the boundary beyond which events become forever invisible to the outside universe. No light or information from beyond this boundary can ever reach external observers, no matter how long they wait or how sensitive their instruments become. This creates a fundamental separation in the cosmos, two regions of spacetime that can never communicate once the horizon forms. From our perspective outside, if we could watch a spacecraft approaching a black hole, we would see something strange and beautiful. As the spacecraft nears the event horizon, it would appear to slow down. This clock would tick slower and slower compared to ours. The light from the spacecraft would shift toward longer, redder wavelengths, dimming gradually. The spacecraft would approach but never quite seem to reach the horizon, appearing to freeze just outside it, fading from view over time but never quite disappearing. We would never see it cross. Yet, from the perspective of those aboard the spacecraft, the experience would be entirely different. Their clocks would tick normally, at least from their point of view. They would cross the event horizon in a finite time, seconds, minutes, or hours depending on the black hole's mass, noticing no local barrier or sudden change at the moment of crossing. For a sufficiently large black hole, the event horizon is not a place of violent forces, but rather an invisible boundary that one could cross as smoothly as passing through a doorway. This divergence between perspectives is one of the beautiful puzzles that black holes present to our understanding of reality. This difference in how time flows near a black hole is not an illusion but a fundamental aspect of how the universe works. Einstein's theory tells us that gravity and acceleration affect the passage of time itself. Near a black hole, where gravity becomes extraordinarily strong, time dilation becomes extreme. A clock held closer to a black hole ticks slower than one held farther away, when both are compared to a distant reference clock. This has been confirmed by precise experiments near Earth, where atomic clocks at different altitudes measure time passing at slightly different rates. Near a black hole, this effect amplifies to dramatic extremes. If you could somehow orbit close to a black hole's event horizon for a while, then return to Earth, you would find that much more time had passed on Earth than you experienced. Hours for you might correspond to years or decades on Earth. You would have traveled, in a sense, to Earth's future, a one-way journey through time made possible by gravity's effect on spacetime. This is not science fiction, but a consequence of well-tested physics. Astronauts on the International Space Station experience a tiny version of this effect. They age slightly slower than people on Earth's surface, though the difference is only fractions of a second over months in orbit. Near a black hole, the effect becomes profound. The extreme curvature of spacetime near the event horizon creates a gradient in how time flows, and this gradient has real, measurable consequences for anything experiencing it. As we continue deeper into understanding black holes, we must carry with us this insight that time itself is flexible, flowing at different rates depending on gravity's strength. Beyond the event horizon lies the interior of a black hole, a region forever hidden from external view. What exists there remains one of physics' deepest mysteries, yet our mathematical theories allow us to explore it in equations even if we cannot observe it directly. Inside the event horizon, something profound happens to the nature of space and time. They exchange their roles in a certain mathematical sense. Outside a black hole, you are free to move through space in any direction, but you are always carried forward through time. Inside the horizon, the radial direction pointing toward the center becomes time-like, meaning you are drawn inevitably toward the center just as you are normally drawn inevitably forward through time. Moving toward the center is no longer a choice you can avoid through maneuvering. It becomes as unavoidable as tomorrow. At the very center of this region, our equations predict what we call a singularity, a point or region where space-time curvature becomes infinite, where density becomes infinite, where the smooth fabric of space-time seems to tear. For a non-rotating black hole, this singularity is predicted to be a point. For a rotating black hole, which is what we expect most real black holes to be, the mathematics suggests the singularity forms a ring. Yet most physicists believe these infinite values are not physically real but rather signposts indicating where our current theories break down. General relativity, which describes gravity so accurately in most circumstances, likely cannot describe conditions at such extreme densities without incorporating quantum mechanics. A complete theory of quantum gravity, which we have not yet formulated, would presumably replace the singularity with something finite, perhaps a region of quantum foam, perhaps a structure we cannot yet imagine. For now, the singularity remains a mystery wrapped within a mystery, hidden behind the event horizon's veil. The properties that a black hole retains from its formation are remarkably few. This simplicity is encapsulated in what physicists call the No-Hair Theorem, a somewhat playful name for a profound principle. The theorem states that black holes are characterized by only three quantities: mass, electric charge, and angular momentum, which is a measure of rotation. Everything else about the star that formed the black hole, its chemical composition, magnetic field, surface features, internal structure, is lost during collapse. Two black holes with identical mass, charge, and spin are absolutely identical, regardless of whether one formed from a star made of hydrogen and the other from a star made of iron. The original star's complexity collapses into geometric simplicity. In practice, black holes in nature are expected to have essentially zero net electric charge. Any charge would quickly attract opposite charges from the surrounding plasma, neutralizing the black hole. What remains then are mass and spin. The mass determines the size of the event horizon and the strength of the black hole's gravitational field. More massive black holes have larger horizons and pull more strongly at any given distance. The spin, or angular momentum, determines how the black hole rotates and affects the geometry of spacetime around it. A spinning black hole drags spacetime around with it in a phenomenon called frame dragging. Close to a rotating black hole, it becomes impossible to remain stationary. You are forced to orbit in the direction of the black hole's spin, like a leaf caught in a whirlpool. This effect occurs in a region outside the event horizon called the ergosphere, where the dragging of spacetime becomes extreme enough that nothing can resist being pulled along. Understanding these properties helps us grasp how elegantly simple black holes are beneath their mysterious nature. When matter falls toward a black hole, it rarely plunges straight in. Instead, it typically carries some angular momentum, some sideways motion that prevents direct radial infall. This matter spirals inward, gradually getting closer to the event horizon while orbiting around it. As it does so, it forms a structure called an accretion disk, a rotating disk of gas, dust, and plasma that gradually spirals into the black hole. This disk is where much of the observable activity around black holes occurs. Friction within the disk, as material at different distances orbits at different speeds, generates tremendous heat. The inner regions of the disk, moving at significant fractions of light speed and heated to millions of degrees, glow intensely in X-rays and ultraviolet light. This radiation is not coming from the black hole itself. The event horizon emits nothing, but from the material just before it crosses the horizon. A black hole actively feeding on surrounding matter can be surrounded by one of the brightest structures in the universe, paradoxically making these dark objects among the most luminous phenomena we observe. The disk itself is relatively thin compared to its diameter, much like the rings of Saturn but vastly larger and hotter. For stellar mass black holes, the inner edge of the accretion disk lies just a few times the event horizon's radius. For supermassive black holes, accretion disks can extend for billions of kilometers. Material in the disk gradually loses angular momentum through complex magnetic and friction processes, allowing it to spiral ever closer until it finally crosses the event horizon and disappears from our view. This accretion process is not only visually spectacular but also provides the primary way we detect and study black holes, through the intense radiation their accretion disks emit. Some accreting black holes produce another remarkable phenomenon: jets. These are narrow beams of particles and energy that shoot outward from near the black hole's poles, perpendicular to the accretion disk, at speeds approaching that of light. These jets can extend for hundreds of thousands or even millions of light years, far beyond the galaxy containing the black hole, creating some of the largest structures associated with individual objects in the universe. The formation of jets involves the complex interaction between the black hole's spin, the accretion disk, and powerful magnetic fields threading through the disk. As the disk rotates, it twists magnetic field lines into coils and ropes of electromagnetic energy. These twisted fields channel some of the infalling material away from the black hole, accelerating it to relativistic speeds along the rotation axis. The exact mechanisms are still being refined by astrophysicists, but observations confirm that the most powerful jets are associated with rapidly spinning black holes and strong magnetic fields. The energy powering these jets ultimately comes from the gravitational energy of material falling into the black hole, and in some models, from the rotational energy of the black hole itself through a process called the Blandford-Znajek mechanism. Despite the immense distances jets traverse, they remain relatively narrow, focused by the magnetic fields that confine them. When jets from supermassive black holes slam into the intergalactic medium, they create enormous cavities and shock waves, heating the surrounding gas to tens of millions of degrees. These jets play a significant role in galaxy evolution, preventing gas from cooling and forming stars in certain regions. The presence of jets transforms black holes from mere endpoints of gravitational collapse into active participants in shaping their cosmic neighborhoods, influencing star formation and galaxy development across vast distances. Black holes exist across an enormous range of masses, from a few times the sun's mass to billions of solar masses. The smallest black holes we know of contain perhaps 3 to 5 times the mass of our sun, compressed within an event horizon just a few kilometers across. These stellar mass black holes are the remnants of massive stars, as we discussed earlier. They are scattered throughout galaxies wherever massive stars have lived and died. Our galaxy likely contains tens of millions of these stellar mass black holes, though detecting them is challenging because they emit no light themselves. We find them primarily when they have companion stars from which they can pull material, creating accretion disks that shine in X-rays. At the other extreme are the supermassive black holes that inhabit the centers of most large galaxies, including our own Milky Way. These giants contain millions to billions of solar masses. The black hole at our galaxy's center, Sagittarius A*, contains about 4 million solar masses and has an event horizon roughly as large as Mercury's orbit. Other galaxies host even larger black holes. Some contain tens of billions of solar masses, with event horizons that could encompass our entire solar system. How these supermassive black holes form remains an active area of research. They appear to have existed very early in the universe's history, when galaxies were young, suggesting they grew rapidly through some combination of continuous feeding and mergers with other black holes. Between these extremes may exist intermediate mass black holes, containing hundreds to hundreds of thousands of solar masses. Though these are more difficult to detect and confirm, the diversity of black hole masses reflects the variety of ways they can form and grow over cosmic time. The supermassive black hole at the center of our Milky Way galaxy offers us a nearby laboratory for studying these objects. Though nearby is relative, it sits about 26,000 light-years away. This is close enough that we can observe stars orbiting around it with great precision. For over 25 years, astronomers have tracked these stars as they loop around the invisible massive object at the galaxy's heart. One star, designated S2, follows an elliptical orbit that brings it within about 17 light-hours of the black hole, roughly the distance from the Sun to Neptune, every 16 years. At its closest approach, S2 reaches speeds of about 5,000 kilometers per second, fast enough to cross the distance from Earth to the Moon in less than a minute. These orbital observations allow astronomers to precisely measure the central black hole's mass and confirm that it must be an incredibly compact object. No other known explanation fits the data. The star's motion around the black hole follows the predictions of general relativity with remarkable accuracy, providing tests of Einstein's theory in a strong gravitational field. In 2019, astronomers achieved something extraordinary. They obtained the first image of the region around Sagittarius A*, not from our own galaxy but from the supermassive black hole in the galaxy M87, using a network of radio telescopes spanning the Earth. This image showed a dark shadow, the black hole itself, surrounded by a bright ring of emission from the accretion disk. This shadow is slightly larger than the event horizon due to gravitational lensing, where light paths curve around the black hole. This observation confirmed that the object truly has an event horizon and that its properties match theoretical predictions with stunning precision, giving us our first direct visual evidence of a black hole's shadow against the glowing matter around it. Black holes, for all their apparent stillness, can be quite dynamic when they interact. Throughout cosmic history, black holes have encountered and merged with one another, creating some of the most energetic events since the Big Bang. When two black holes orbit each other, they form a binary system held together by their mutual gravitational attraction. As they orbit, they emit gravitational waves, ripples in spacetime itself, predicted by Einstein and first directly detected in 2015 by the LIGO Observatory. These waves carry energy away from the system, causing the orbit to gradually decay. The black holes spiral closer and closer together over millions or billions of years. As they approach each other, the orbital period shortens and the gravitational waves strengthen. In the final moments before merger, the two black holes whip around each other dozens or hundreds of times per second, creating intense gravitational wave signals. When they finally collide and merge, they form a single, larger black hole. The newly formed black hole rings like a struck bell, its event horizon oscillating before settling down to a smooth, stationary state. During this brief merger, the system can emit more power in gravitational waves than all the stars in the observable universe combined, though only for a fraction of a second. The mass of the final black hole is slightly less than the sum of the two original black holes. Some mass converts to energy carried away by gravitational waves, following Einstein's famous equation E=mc². These gravitational wave observations have opened a new window on the universe, allowing us to detect events that produce no light or other electromagnetic radiation. We can now listen to the universe's gravitational symphony, hearing black holes merge in distant galaxies and learning about their properties from the signals they produce as space-time itself vibrates around them. The gravitational waves from merging black holes are extraordinarily faint by the time they reach Earth. When two black holes collided 1.3 billion light-years away in the event detected in 2015, the passing gravitational wave stretched and compressed space by less than 1,000th of the diameter of a proton. Yet our instruments, marvels of precision engineering, detected this whisper from across the cosmos. The LIGO detectors use laser beams traveling along 4-kilometer arms to measure these minute changes in distance. When a gravitational wave passes, it stretches space in one direction while compressing it in the perpendicular direction. By comparing the time it takes light to travel along the two perpendicular arms, the detectors can sense these tiny distortions. The signal from a black hole merger rises in frequency and amplitude as the orbital period shortens, a pattern called a chirp. This chirp lasts only a fraction of a second for stellar mass black holes, but contains a wealth of information about the masses, spins, and distance of the merging objects. Since that first detection, dozens of black hole mergers have been observed, revealing a population of black holes across a range of masses and teaching us about how common these mergers are in the universe. Some mergers have surprised astronomers by involving black holes more massive than expected from stellar evolution alone, suggesting our understanding of how massive stars die may need refinement. Each detection is not just an observation but a test of general relativity in extreme conditions, and so far, Einstein's century-old theory continues to pass every test with remarkable accuracy. These observations mark the beginning of gravitational wave astronomy, a new way of observing the cosmos that complements traditional telescopes and promises discoveries we cannot yet anticipate. While black holes themselves emit no light, their effects on surrounding matter create some of the brightest objects in the universe. When a supermassive black hole at the center of a galaxy actively accretes matter at high rates, it can shine with the luminosity of trillions of suns. These active galactic nuclei, or AGN, are so bright they can outshine all the stars in their host galaxies combined. The most luminous examples are called quasars, a name derived from quasi-stellar radio sources, because they appeared as point-like sources in early observations. Quasars were most common when the universe was younger, between 2 and 4 billion years old, though some exist today as well. The light from quasars can travel across most of the observable universe, making them visible at immense distances. Some quasars we observe are so far away that we see them as they existed more than 13 billion years ago, when the universe was less than 1 billion years old. This tells us that supermassive black holes and their accretion processes were already well established early in cosmic history. The energy powering quasars comes from gravitational potential energy. As matter falls into the black hole, it releases energy far more efficiently than nuclear fusion. A black hole converting infalling matter to radiation is roughly 10 times more efficient than the sun's fusion process. However, quasars are not continuously active. They require a steady supply of matter to fuel their brilliance. When the surrounding gas is exhausted or blown away by the radiation pressure itself, the quasar fades, and the black hole becomes quiescent. The supermassive black hole at the center of our Milky Way is currently in this quiet phase, accreting matter at a trickle compared to its maximum capacity, producing only modest amounts of radiation rather than blazing as a quasar does. Black holes play a significant role in the evolution of galaxies, influencing star formation across vast distances despite their relatively small size. The energy released by matter falling into supermassive black holes can heat or blow away the gas that would otherwise cool and form new stars. This process, called AGN feedback, appears to regulate galaxy growth. Without it, theoretical models predict that massive galaxies would contain far more stars than we actually observe. The jets and winds driven by active black holes can extend for hundreds of thousands of light-years, far beyond the galaxy itself, heating the intergalactic gas and preventing it from falling into the galaxy to form stars. In galaxy clusters, where many galaxies congregate, the central massive galaxy often contains a supermassive black hole that episodically produces powerful jets. These jets excavate enormous cavities in the hot gas surrounding the cluster, visible as dark regions in X-ray observations where the jets have pushed the gas aside. This heating prevents the gas from cooling and flowing into the central galaxy, limiting star formation. Observations reveal a tight correlation between the mass of supermassive black holes and properties of their host galaxies, particularly the mass of the central bulge of stars. More massive bulges contain more massive black holes, following a consistent relationship. This correlation suggests that black holes and galaxies co-evolve, influencing each other's growth through feedback processes. The black hole grows by accreting matter, releases energy that affects the surrounding gas, which in turn affects the galaxy's ability to form stars and accrete more matter onto the black hole. This interconnected evolution means that understanding galaxies requires understanding their central black holes, and vice versa. For most of the time since black holes were first predicted mathematically, they remained theoretical objects, solutions to equations but not confirmed as real physical objects in the universe. The evidence slowly accumulated through various indirect observations. Astronomers detected X-ray sources that varied rapidly, suggesting compact objects. They observed stars orbiting invisible massive companions. They measured jets and radiation from galactic centers that required extraordinary energy sources. Each observation added to the case, but definitive proof remained elusive because black holes emit no light themselves. The breakthrough came in several stages. Gravitational wave detections from LIGO beginning in 2015 provided strong evidence for stellar mass black holes by directly observing their mergers. The signals matched theoretical predictions so precisely that alternative explanations became untenable. Then, in 2019, the Event Horizon Telescope collaboration released the first image of a black hole shadow, specifically the supermassive black hole in the center of the galaxy M87. This image showed a dark central region surrounded by a bright ring of emission, matching predictions from general relativity for how a black hole should appear. The dark region, the shadow, is created by the event horizon and the extreme bending of light around it. Photons can orbit a black hole at a radius about 1.5 times the event horizon radius, creating a photon sphere. The shadow we see is actually larger than the event horizon itself due to this light bending effect. In 2022, the Event Horizon Telescope followed up with an image of Sagittarius A*, the black hole at our own galaxy's center, confirming that it too possesses an event horizon and properties consistent with a black hole. These images represent the culmination of decades of theoretical work and observational ingenuity, transforming black holes from mathematical abstractions to observed reality. The discovery that fundamentally changed our understanding of black holes came in 1974, when Stephen Hawking published calculations showing that black holes are not entirely black. Quantum effects near the event horizon cause black holes to emit radiation and gradually evaporate over time. This Hawking radiation emerges from a subtle interplay between quantum mechanics and gravity. In quantum field theory, even empty space is not truly empty. Particle-antiparticle pairs constantly pop into existence and quickly annihilate. This happens everywhere, all the time, as a consequence of quantum uncertainty. Usually, these virtual particles exist for such a brief time that they have no observable effect. But near a black hole's event horizon, something different can occur. If a particle-antiparticle pair forms just outside the horizon, One particle might fall into the black hole while the other escapes to infinity. To an outside observer, it appears that the black hole has emitted a particle. The energy for this particle comes from the black hole's mass, so the black hole loses a tiny amount of mass with each emission. Over time, this process causes the black hole to shrink. The temperature of this radiation is inversely proportional to the black hole's mass. Larger black holes are colder, smaller black holes are hotter. For stellar mass and supermassive black holes, this temperature is incredibly low, far colder than the cosmic microwave background radiation that fills space. Such black holes absorb more energy from the universe than they emit through Hawking radiation, so they actually grow rather than shrink in the current epoch. But as the universe continues to expand and cool, eventually even these black holes will begin to lose mass. The evaporation accelerates as the black hole shrinks. Smaller black holes are hotter and radiate faster, creating a runaway process that ends in the black hole's complete evaporation. The timescale for black hole evaporation is almost incomprehensibly long for any black hole of stellar mass or larger. A black hole with the mass of our Sun would take about 10 to the 67th power years to evaporate completely. That's a 1 followed by 67 zeros. For comparison, the current age of the universe is merely 1.4 times 10 to the 10th power years. The Sun-mass black hole would persist for a time span 10 billion times longer than the universe has currently existed. For supermassive black holes, the timescales are even more extreme. A billion solar mass black hole would require approximately 10 to the 100th power years to evaporate. A span of time so vast that it defies intuitive understanding. To put this in perspective, by the time such a black hole evaporates, the universe will have expanded and cooled so much that it will be nearly empty, with structures long dissolved, stars long dead, and only the thinnest soup of particles remaining. Despite these enormous timescales, the process is real and unavoidable according to our current understanding of physics. As a black hole evaporates, its temperature rises because temperature is inversely related to mass. When the black hole shrinks to planetary masses, the process accelerates. By the time it reaches the mass of a mountain, it's radiating intensely, glowing white-hot. In the final moments, when the black hole has shrunk to microscopic scales, it explodes in a burst of radiation, releasing its remaining mass energy in a fraction of a second. The final flash would be extraordinarily energetic, though we will never observe one from a black hole formed by natural stellar collapse. The timescales are too long. However, if tiny primordial black holes formed in the early universe, some of them might be evaporating now, and we search for signs of their final explosions. Hawking's discovery that black holes radiate and evaporate leads to a profound puzzle known as the information paradox. In quantum mechanics, information is never truly lost. The quantum state of a system determines its past and future completely, and this information must be preserved even as the system evolves. But when matter falls into a black hole, it seems to carry its quantum information across the event horizon, where it becomes forever inaccessible to the outside universe. If the black hole later evaporates completely through Hawking radiation, releasing only thermal radiation that contains no information about what fell in, then the information appears to have been destroyed. This violates a fundamental principle of quantum mechanics, creating a deep conflict between quantum theory and general relativity. The paradox has motivated decades of theoretical work. Some physicists propose that information is gradually encoded in subtle correlations within the Hawking radiation, though this seems to require information to escape from behind the event horizon in ways that general relativity does not allow. Others suggested that the event horizon might not be as smooth as general relativity predicts. There might be a firewall of high-energy particles at the horizon that destroys information-carrying matter before it enters. This would preserve information but violates another principle called equivalence, which says that freely falling observers should notice nothing special when crossing the horizon of a sufficiently large black hole. More recent work in string theory and holography suggests that the information paradox might be resolved by recognizing that the three-dimensional interior of a black hole is somehow encoded in the two-dimensional surface of the event horizon, though the details remain under active investigation. The information paradox sits at the intersection of our two most successful physical theories, suggesting that resolving it will require new. The concept of entropy provides another window into the nature of black holes. Entropy is a measure of disorder, or, more precisely, the number of microscopic states corresponding to a macroscopic system's observable properties. In the early 1970s, Jacob Bekenstein proposed that black holes must have entropy proportional to the area of their event horizons, not their volumes as one might expect. Stephen Hawking's subsequent discovery of black hole radiation confirmed this, providing a precise formula for black hole entropy. It equals 1/4 of the event horizon's area measured in Planck units. This Bekenstein-Hawking entropy is enormous even for stellar mass black holes, vastly exceeding the entropy of the star that collapsed to form the black hole. The fact that entropy is proportional to area rather than volume is surprising and significant. It suggests that the maximum information content of any region of space is determined by the area of the surface bounding that region, not the volume within, a principle that has been generalized as the holographic principle. This principle, inspired by black hole thermodynamics, proposes that our three-dimensional universe might be described by information encoded on a two-dimensional surface, like a hologram encoding three-dimensional images. Black holes thus serve as theoretical laboratories for exploring fundamental questions about information, entropy, and the structure of spacetime. They obey laws of thermodynamics that closely parallel the classical laws. Black holes have temperature through Hawking radiation, entropy, proportional to horizon area, and they satisfy conservation laws. The Zeroth law of black hole mechanics states that surface gravity is constant across the event horizon. The first law relates changes in mass, area, and angular momentum. The second law states that the total horizon area never decreases in classical processes. These parallels between black hole mechanics and thermodynamics suggest deep. In the unimaginably distant future, long after all stars have burned out and galaxies have dispersed, black holes will be among the last remaining objects in the universe. This era, beginning perhaps 10 to the 40th power years from now, is called the black hole era in some cosmological timelines. During this time, the universe will be cold, dark, and nearly empty. The cosmic microwave background radiation will have cooled to a fraction of a degree above absolute zero through cosmic expansion. Any remaining matter will be in the form of black holes of various masses, from stellar remnants to supermassive giants, scattered through an ever-expanding space. Even in this era, slow processes continue. Occasionally, black holes might encounter each other and merge, growing slightly. More rarely, they might capture wandering particles from the thin gas remaining in space. But primarily, they will wait, slowly radiating away their mass through Hawking radiation. For most of this era, the radiation will be incredibly faint. The temperature of stellar mass black holes will be far below the background temperature of space, so they'll actually absorb more energy than they emit. But as the universe continues to expand and cool, eventually the background temperature will drop below the black hole's Hawking temperature, and net evaporation will begin. The smallest black holes will evaporate first, over timescales of 10 to the 67th power years or so. Larger black holes will follow over longer times. Supermassive black holes will be the last significant structures to evaporate, persisting for 10 to the 100th power years or longer before finally vanishing in brief flashes of radiation. After the last black hole evaporates, the universe will contain only dilute radiation and perhaps scattered elementary particles, separated by ever-increasing distances as expansion continues. This far future is one of profound stillness and cold, yet it demonstrates that even understanding what happens inside a black hole's event horizon requires us to think carefully about the nature of spacetime. Outside the horizon, space and time have their familiar characteristics. You can move freely through space in any direction, but you move inexorably forward through time. Inside the horizon, this relationship changes in a profound way. The direction pointing toward the singularity becomes time-like, meaning that moving toward it is like moving forward through time, unavoidable and inevitable. You cannot stop or turn around any more than you can stop time from flowing. All possible paths through spacetime, once inside the horizon, lead to the singularity within a finite time. For a non-rotating Schwarzschild black hole, this time from horizon crossing to singularity is very short, a few microseconds for a stellar mass black hole. For rotating Kerr black holes, which are more realistic since they form from spinning stellar cores, the interior geometry is more complex and includes regions where strange causal structures might exist, though most physicists believe these exotic features are unstable or unphysical. The journey from horizon to singularity would be marked by increasing tidal forces, differences in gravitational pull across your body. For stellar mass black holes, these forces become lethal well before you reach the singularity. Your body would be stretched radially and compressed laterally, in a process colorfully termed spaghettification. For supermassive black holes, the tidal forces at the horizon are relatively gentle, and you could survive crossing and falling for some time before the forces grew strong enough to be harmful. As you approach the singularity, tidal forces grow without limit, ultimately overwhelming any structure. But before reaching the singularity, our description breaks down. Quantum effects should become important at Planck scales, and we lack a complete theory to describe what happens then. The question of what replaces the singularity in a full quantum theory of gravity remains open, but several approaches offer possibilities. In loop quantum gravity, spacetime itself is quantized. It comes in discrete units at the Planck scale rather than being infinitely divisible. In this framework, the singularity might be replaced by a region of maximum but finite curvature, perhaps involving a quantum bounce that connects the black hole interior to another region of spacetime. String theory suggests that the fundamental constituents of reality are not point particles but tiny vibrating strings. At the energies and densities near what would classically be a singularity, string physics becomes relevant, and the singularity might be resolved into a complex but finite structure involving strings and higher dimensional objects called branes. Some approaches propose that the singularity might be a gateway or connection point, though such speculations venture beyond what can currently be tested. What all these approaches share is the recognition that the classical singularity predicted by general relativity is probably not the end of the story. It marks the point where general relativity must give way to quantum gravity. The singularity serves as a beacon, pointing toward new physics that operates at the extreme limits of spacetime. In a sense, every black hole contains within it a laboratory for physics beyond our current theories, though this laboratory is forever sealed from our observation by the event horizon. We can theorize about what happens at the singularity, test our ideas with mathematics, and refine our understanding of quantum gravity, but we cannot directly observe these extreme conditions. The singularity remains one of nature's deepest mysteries, a boundary of knowledge hidden at the heart of every black hole. The formation of supermassive black holes in the early universe presents a puzzle that astronomers are still working to fully resolve. We observe quasars powered by billion solar mass black holes when the universe was less than a billion years old. Yet growing a black hole to such enormous size in the available time is challenging. If a stellar mass black hole formed from the first generation of stars, it would need to accrete matter and grow continuously at nearly the maximum possible rate, called the Eddington limit, to reach a billion solar masses so quickly. The Eddington limit is set by radiation pressure. As matter falls into a black hole and heats up, it emits radiation that pushes back against infalling material. If accretion proceeds too rapidly, the radiation becomes so intense that it halts further infall. For continuous growth at the Eddington limit, a black hole's mass doubles every few tens of millions of years. Starting from 100 solar mass seed, it would take nearly a billion years to reach a billion solar masses, leaving little time for the formation and early growth phases. This suggests that either supermassive black holes found ways to exceed the Eddington limit through special circumstances, or they formed from larger seeds. Direct collapse of massive gas clouds in the early universe could potentially create seed black holes of 10,000 to a million solar masses, giving them a head start. Alternatively, dense star clusters in early galaxies might have undergone runaway collisions and mergers, forming intermediate mass black holes that then grew through accretion. Some combination of these processes probably occurred, with different formation pathways being more or less important in different environments. Understanding supermassive black hole formation requires us to understand conditions in the very early universe, making these objects windows not just into extreme gravity but also into cosmic history. Black holes can exist across an enormous range of sizes, and between stellar mass and supermassive black holes, there might be a population of intermediate mass black holes containing hundreds to hundreds of thousands of solar masses. These objects are harder to detect than stellar mass black holes in X-ray binaries or supermassive black holes in galactic centers, so their existence and abundance remain uncertain. Some globular clusters, dense spheres of ancient stars orbiting in galactic halos, show velocity patterns suggesting central intermediate mass black holes. Certain ultraluminous X-ray sources, which are too bright to be powered by stellar mass black holes accreting at normal rates, might be intermediate mass black holes. Occasionally, gravitational wave detections hint at black holes in this mass range. If they exist in substantial numbers, intermediate mass black holes could serve as the seeds for supermassive black holes, or they might represent a separate population formed through different processes, perhaps in the dense cores of massive star clusters where stellar collisions and mergers could build up larger black holes before the cluster disperses. The question of intermediate mass black holes touches on broader questions about black hole demographics. How many black holes of each mass exist, how they're distributed through space, and what processes create them. Each mass range might have different formation mechanisms and evolutionary paths. Stellar mass black holes form from individual massive stars. Supermassive black holes might form from direct collapse or from growth of smaller seeds. Intermediate mass black holes could form in dynamically active stellar environments where collisions are frequent. Together, these populations span 8 or 9 orders of magnitude in mass, from roughly 3 solar masses to tens of billions, each range reflecting different aspects of cosmic evolution and stellar dynamics. The matter surrounding black holes exists in extreme conditions that test our understanding of physics. In the innermost regions of an accretion disk, material orbits at significant fractions of light speed. At such speeds, relativistic effects become important: time dilation, length contraction, and the increase of mass with velocity. The orbits themselves are affected by general relativity in ways that Newtonian gravity doesn't predict. The innermost stable circular orbit around a non-rotating black hole lies at 3 times the Schwarzschild radius, or about 1.5 times the event horizon radius. Inside this radius, no stable orbits exist. material inevitably spirals inward and crosses the event horizon. For rotating black holes, the innermost stable orbit's location depends on the spin and whether the orbit is prograde, rotating in the same direction as the black hole, or retrograde, opposite direction. Prograde orbits can exist closer to the event horizon for rapidly spinning black holes, allowing matter to orbit nearer and reach higher temperatures before plunging in. This affects the spectrum of radiation from the accretion disk. The inner edge's location and temperature depend on the black hole's spin, so by observing the disk spectrum carefully, astronomers can measure black hole spin. The material in these inner regions experiences extreme tidal forces, intense radiation, powerful magnetic fields, and temperatures reaching tens of millions of degrees. Atoms are stripped of electrons, existing as bare nuclei in a fully ionized plasma. This environment is far removed from anything we experience on Earth, yet we can model it using physics and compare predictions with observations. The agreement between theoretical models of accretion disk structure and observed spectra gives us confidence that we understand these extreme environments reasonably well, though many details remain uncertain and require ongoing research. Magnetic fields play a crucial role in accretion disk dynamics and jet formation around black holes. Although black holes themselves have no magnetic field, the No-Hair Theorem ensures they retain no magnetic charge. The ionized plasma in accretion disks carries magnetic fields with it. As the disk rotates and turbulent motions stir the plasma, magnetic field lines become twisted and amplified. These fields transport angular momentum outward through the disk, allowing material to spiral inward. The magnetorotational instability, discovered through computer simulations, shows how weak magnetic fields in rotating plasma can grow and create turbulence that enables accretion. This process is essential for understanding how matter actually loses angular momentum and falls into black holes. Without it, friction alone would be insufficient. The magnetic fields also provide the scaffolding for launching jets. Field lines threading through the disk can be twisted by the disk's rotation into helical structures that channel plasma outward along the black hole's spin axis. The precise mechanisms are complex and involve magnetohydrodynamics, the physics of how magnetic fields and electrically conducting fluids interact. Computer simulations of magnetized accretion flows show structures and behaviors that match observations, including disk turbulence, variable accretion rates, and jet formation. These simulations require tremendous computing power because they must resolve a wide range of scales, from the event horizon to the outer disk, and follow the complex interplay of gravity, magnetic forces, and plasma physics. Understanding accretion and jet formation is not just an academic exercise. These processes are fundamental to how black holes grow, how they affect their environments, and how energy flows in the universe. The study of black hole accretion connects astrophysics, plasma physics, and relativity in a beautiful synthesis of physical principles. When we observe the universe, we find that supermassive black holes are nearly ubiquitous in the centers of large galaxies. This wasn't always known. Only in the 1990s and 2000s did observations of stellar velocities near galactic centers, combined with improved understanding of galaxy dynamics, establish that most galaxies harbor central supermassive black holes. Our Milky Way has one, Andromeda has one, and surveys of galaxies show that the presence and mass of central black holes follows predictable patterns. This ubiquity suggests that black hole formation and galaxy formation are intimately connected processes. In the early universe, as the first galaxies assembled from collapsing gas clouds, conditions apparently favored the formation of massive black holes in their centers. Once formed, these black holes grew along with their host galaxies, fed by gas funneled toward the galactic center through mergers, instabilities, and gravitational interactions. The tight correlations between black hole mass and galaxy properties, particularly the mass of the central stellar bulge, suggest a self-regulating feedback process. As the black hole grows and accretes, the energy it releases affects the surrounding galaxy, heating or expelling gas and regulating star formation. This feedback limits both the black hole's growth by removing its fuel supply and the galaxy's growth by preventing gas from cooling and forming new stars. The end result is a correlation between black hole mass and bulge mass that holds across a wide range of galaxy sizes. Understanding this coevolution requires modeling galaxy formation over billions of years, tracking gas flows, star formation, black hole accretion, and feedback effects in a complex, interconnected system. Observations of distant galaxies at different cosmic epochs allow us to trace this coevolution through time, seeing how black holes and galaxies grew together from the early universe to the present day. The process of matter falling into a black hole is not steady but often variable and episodic. Accretion rates fluctuate due to variations in the supply of gas, instabilities in the accretion disk, and the complex magneto-hydrodynamic processes occurring near the black hole. These variations cause corresponding fluctuations in the radiation emitted by the accretion disk and surrounding regions. We observe this variability across the electromagnetic spectrum, from radio waves through visible light to X-rays and gamma rays. Some variations occur on timescales of years or decades, reflecting large-scale changes in gas supply. Others occur much faster. Stellar mass black holes in X-ray binaries can show flickering on timescales of milliseconds, reflecting processes very close to the event horizon where orbital periods are short and light travel times are brief. These rapid variations provide information about the size and structure of the emitting region, since variability faster than a certain timescale indicates the source must be smaller than light travels in that time. For supermassive black holes, variability timescales range from hours to years, with the fastest variations telling us about the innermost regions of the accretion flow. Some black holes undergo dramatic outbursts, brightening by factors of 100 or more over months or years. These outbursts might be triggered by tidal disruption events, where a star wanders too close to the black hole and is torn apart by tidal forces. The stellar debris forms an accretion disk and produces a bright flare as it falls into the black hole over months to years. Such events are rare for any given galaxy, perhaps once every 10,000 to 100,000 years, but in surveys of many galaxies, astronomers detect several per year. Each tidal disruption event provides an opportunity to study black hole accretion in detail and to discover previously quiescent black holes in galactic centers. The study of black holes has required pushing observational techniques to their limits and developing new technologies to detect faint signals and resolve tiny angular scales. Early evidence for black holes came from X-ray observations. Satellites like Uhuru in the 1970s detected X-ray binary systems where compact objects, presumably black holes or neutron stars, were accreting matter from companion stars. Distinguishing black holes from neutron stars required measuring or constraining the compact object's mass, since masses above about 3 solar masses are too large for neutron stars. Observations of gas motions in galactic centers, using spectroscopy to measure Doppler shifts, revealed massive compact objects that couldn't be explained as clusters of stars or other conventional objects. They had to be black holes. The development of infrared astronomy allowed observations through the dust obscuring the Milky Way's center, enabling decade-long studies of stellar orbits around Sagittarius A star. Radio astronomy, especially very long baseline interferometry, where radio telescopes across continents or around the world combine their signals, achieved the angular resolution needed to image the shadows of supermassive black holes. The LIGO gravitational wave detectors represented a triumph of precision engineering, measuring distance changes smaller than a proton's diameter to detect spacetime ripples from distant black hole mergers. Each advance in observation has been matched by theoretical progress. As researchers developed better models of black hole physics, accretion processes, relativistic jet formation, and gravitational wave generation. The interplay between observation and theory has been essential. Observations guide theoretical development by revealing unexpected phenomena, while theory guides observations by predicting what to look for and where to look. This synergy has transformed black holes from speculative solutions to Einstein's equations into well-study. In our exploration of black holes, we often focus on their exotic physics and extreme conditions, but they also serve as cosmic tools for understanding the universe. The gravitational lensing caused by black holes and their host galaxies can magnify distant objects, allowing us to observe things we couldn't otherwise detect. While individual stellar mass black holes rarely cause observable lensing, supermassive black holes at the centers of galaxies contribute to the lensing effects we observe when distant galaxies are magnified by foreground galaxy clusters. Studying this lensing provides information about the mass distribution in the foreground, including dark matter as well as ordinary matter. Black holes also serve as laboratories for testing general relativity in strong field regimes. The orbits of stars around Sagittarius A*, the properties of gravitational waves from merging black holes, and the shadow of M87's black hole all provide tests of Einstein's theory under conditions far more extreme than we can create in laboratories. So far, general relativity has passed every test with remarkable precision, but physicists continue to search for any deviations that might point toward new physics beyond general relativity. Black holes also help us understand the interstellar and intergalactic medium, the gas and dust between stars and galaxies. The jets and winds from active black holes stir and heat this medium, affecting its properties over large volumes. By studying how these processes work, we learn about the life cycle of baryonic matter in the universe, how it cycles between diffuse gas, stars, and compact objects. The role of black holes in this cosmic ecology is significant despite their small size relative to galaxies. They punch above their weight in terms of energetic influence. As we continue to study black holes through multiple observational windows, electromagnetic radiation, gravitational waves, neutrinos, and perhaps someday other messengers, we gain the concept of the photon sphere around a black hole offers insight into how extreme gravity affects light. At a radius of 1.5 times the Schwarzschild radius for a non-rotating black hole, or various radii depending on spin and direction for rotating black holes, photons can orbit in circular paths. These are unstable orbits, meaning that any small perturbation will cause the photon to either fall into the black hole or escape to infinity. A photon must have exactly the right trajectory, tangent to the sphere at that radius, to orbit. If you were somehow positioned at the photon sphere and looked around, you could theoretically see the back of your own head. Light from behind you would orbit the black hole and reach your eyes from the front. This is a thought experiment rather than a practical observation, of course, given that the photon sphere lies outside the event horizon but in a region of extreme gravity and intense radiation from any accretion disk. The photon sphere is significant for observations because it affects how we see black holes. The bright ring in the Event Horizon Telescope images corresponds roughly to the photon sphere. The glowing material of the accretion disk, bent and concentrated by gravitational lensing, creates a bright ring at this radius. The dark interior, the shadow, is larger than the event horizon because it includes not just the horizon itself but also the region where light cannot escape directly to us, being either captured or orbiting before escaping in other directions. The precise size and shape of the shadow depend on the black hole's mass and spin, and potentially on any deviations from general relativity. By measuring these properties carefully, astronomers can test theoretical predictions and search for new physics. The photon sphere reminds us that black holes aren't just dark objects but sculptors of light, creating optical effects unlike anything else in the universe, bending and redirecting light paths in ways that reveal T. Primordial black holes represent a hypothetical population that might have formed in the very early universe, not from stellar collapse but from extreme density fluctuations shortly after the Big Bang. In the first fractions of a second of cosmic history, if some regions were significantly denser than average, they could have collapsed directly into black holes. These primordial black holes could span an enormous range of masses, from microscopic, much smaller than a proton, to thousands of solar masses or more, depending on the size of the density fluctuation. Small primordial black holes are particularly interesting because, unlike stellar mass black holes formed from stars, they could have very low masses and thus would be evaporating through Hawking radiation by now. A primordial black hole with an initial mass around 10 billion tons would be evaporating today, having survived for the universe's current age. Such black holes would be emitting particles and radiation as they shrink, potentially detectable as gamma-ray sources if they happen to be near enough. Searches for these signatures have so far found no convincing candidates, placing limits on how common small primordial black holes can be. Larger primordial black holes, if they exist, might contribute to dark matter, the mysterious substance that makes up most of the matter in the universe but doesn't emit or absorb light. Since primordial black holes are dark and interact only through gravity, they could potentially explain some or all of dark matter. However, various observations constrain this possibility. Gravitational lensing surveys, the dynamics of star clusters, and other observations limit how much of dark matter can be in the form of black holes in various mass ranges. Current evidence suggests that primordial black holes probably don't make up most of dark matter, though they might exist in small numbers. The search continues as finding primordial black holes would be a major discovery. Revealing. The relationship between black holes and quantum mechanics goes beyond Hawking radiation. Some theoretical physicists propose that the event horizon itself might have structure at the quantum level, contrary to the smooth geometry predicted by classical general relativity. One controversial idea is the black hole firewall paradox. This paradox arises from attempts to preserve information in black hole evaporation while maintaining other cherished principles of physics. If information is encoded in correlations between early and late Hawking radiation, and if that radiation is also entangled with its partners that fell into the black hole, this creates a conflict. Quantum mechanics forbids a particle from being maximally entangled with two different systems. One proposed resolution is that the event horizon, rather than being a smooth, unremarkable surface that infalling observers pass through without noticing, might be a violent boundary, a firewall, where quantum effects destroy any structure attempting to cross. This would preserve information but violate the principle that free-falling observers experience nothing special at the horizon of a large black hole. The firewall paradox has generated much debate and no clear consensus. Alternative resolutions involve modifying our understanding of quantum entanglement, or recognizing that the paradox relies on assumptions that break down near black holes, or accepting that some principles we thought fundamental might not apply in these extreme situations. Another approach involves the holographic principle, which suggests that the information about the black hole's interior is encoded on its surface. In this view, the three-dimensional interior might be a kind of projection or reconstruction from two-dimensional information on the event horizon. These ideas push physics into new territory, requiring us to think carefully about the foundations of quantum mechanics, general relativity, and how they might fit together in a When two galaxies merge, their central supermassive black holes eventually sink toward the center of the merged system through a process called dynamical friction. As each black hole moves through the stars and dark matter of the merged galaxy, it gravitationally attracts nearby particles, creating an overdensity wake behind it. This wake gravitationally pulls back on the black hole, causing it to lose orbital energy and spiral inward. Once the two black holes are within a few light years of each other, dynamical friction becomes less efficient, and the final spiral requires other mechanisms, possibly involving interactions with stars on orbits that pass close to both black holes. These interactions can extract energy and angular momentum from the binary, causing it to shrink further. Eventually, the two black holes enter a gravitational wave-dominated regime, where emission of gravitational waves carries away energy faster than any other process. The orbital decay accelerates, and within a relatively short time, perhaps thousands of years for supermassive black holes, the binary merges, forming a single larger black hole. This final merger produces the most powerful gravitational wave bursts in the universe. For supermassive black holes, these waves have lower frequencies than the signals from stellar mass black hole mergers that LIGO detects. Space-based gravitational wave detectors like the planned LISA mission will observe these low-frequency signals, potentially detecting supermassive black hole mergers across cosmic history. Each galaxy merger potentially leads to a black hole merger, so the rate of these events tracks the rate of galaxy mergers throughout cosmic time. Observing supermassive black hole mergers will provide a census of these events and teach us about galaxy merger history, the growth of black holes over time, and the dynamics of how black holes pair up and coalesce in merged galaxies. The far future of black holes is intimately connected with the far future of the universe itself. Current cosmological observations suggest the universe will continue expanding forever, driven by dark energy. As it expands, galaxies outside our local group will recede beyond the cosmic horizon, disappearing from view as their recession velocity exceeds light speed due to the expansion of space itself. Within bound structures like galaxy clusters, this expansion doesn't matter. Gravity holds these systems together. But the universe overall grows larger, colder, and more dilute. Star formation will eventually cease when gas supplies are exhausted, perhaps 10 trillion years from now. Existing stars will burn out. The longest-lived red dwarfs might shine for 10 trillion years, but eventually all stars will fade. White dwarfs will cool to black dwarfs. Neutron stars will remain, gradually cooling. And black holes will persist, growing slowly through occasional captures of wandering objects but primarily just existing, waiting. This is the black hole era. Over timescales we can barely imagine, black holes will be the dominant form of mass in the universe. They will sit in the darkness, separated by ever-increasing distances as space expands, emitting faint Hawking radiation. Eventually, after 10 to the 67th power years for stellar mass black holes and much longer for supermassive ones, they will evaporate completely. The final black hole will disappear perhaps 10 to the 100th power years from now, leaving behind only diffuse radiation and particles in an exponentially expanding space. What comes after the black hole era is even more speculative. Perhaps a universe containing only photons, neutrinos, and electrons, separated by such vast distances that interactions become negligible. Or perhaps vacuum decay will eventually transform space into a lower energy state, though this is highly uncertain. Throughout this journey, we have explored black holes from multiple perspectives: their formation from collapsing stars, their geometric properties as regions of curved spacetime, their observational signatures through accretion disks and gravitational waves, their role in galaxy evolution, and their ultimate fate through quantum evaporation. Each perspective reveals different aspects of these remarkable objects. Black holes challenge our understanding of physics at the most fundamental level, sitting at the intersection of general relativity and quantum mechanics, two pillars of modern physics that have yet to be fully reconciled. They force us to confront questions about the nature of space and time, the fate of information, the meaning of entropy, and the limits of predictability. They demonstrate that the universe contains phenomena stranger than our ancestors ever imagined. Yet these phenomena emerge from straightforward applications of physical laws. There is beauty in how black holes form not through special circumstances, but as inevitable consequences of gravity acting on concentrated mass. There is elegance in how they are described by just a few parameters despite the complexity of their progenitors. There is profundity in how they connect thermodynamics, information theory, and quantum gravity. As we continue to study black holes through ever more sophisticated observations and develop increasingly refined theories, we deepen our understanding not just of these objects but of the universe's fundamental workings. Every observation of a black hole, whether through gravitational waves or electromagnetic radiation or stellar dynamics, adds to our knowledge. Every theoretical advance, whether in quantum gravity or numerical simulations of accretion flows, enhances our comprehension. Black holes are not merely exotic curiosities relegated to the fringes of astrophysics but central players in cosmic evolution. The practical study of black holes has required innovations across multiple fields. Developing gravitational wave detectors like LIGO involved advances in laser technology, materials science, seismology to isolate detectors from environmental vibrations, and signal processing to extract faint gravitational wave signals from noise. Creating the Event Horizon Telescope required coordinating radio telescopes across the world, developing algorithms to combine their data into images, and building computational infrastructure to process petabytes of recorded signals. Understanding accretion disks required advances in computational fluid dynamics, magnetohydrodynamics, and relativistic physics, as well as high-performance computing to run simulations. Each observational or theoretical advance built on previous work, creating a cumulative progression of knowledge. The people involved in black hole research span diverse backgrounds and countries, forming an international community united by curiosity about these objects. From Einstein deriving the field equations of general relativity, to Schwarzschild solving them in the trenches of World War I, to Chandrasekhar understanding stellar collapse on a long sea voyage, to Hawking discovering radiation while investigating quantum field theory in curved spacetime, to the thousands of scientists currently observing, analyzing, and theorizing about black holes, this is a collective human endeavor spanning over a century. Each contribution builds on others, gradually illuminating aspects of black holes that were once obscure. The process is not always smooth. There have been debates, wrong turns, and surprises along the way, but through sustained effort guided by observation and logic, our understanding has deepened remarkably. Today's students learning about black holes can access knowledge that took generations to accumulate, and they will build further on this foundation, perhaps resolving current mysteries and uncovering new puzzles. One of the most profound aspects of black holes is how they embody the unity of physics. To understand them fully requires general relativity to describe spacetime curvature, quantum mechanics to understand Hawking radiation and information paradoxes, thermodynamics to comprehend entropy and temperature, statistical mechanics to interpret black hole microstates, electromagnetism to model radiation from accretion disks, fluid dynamics and plasma physics to understand accretion flows, particle physics to track what happens to matter in extreme conditions, and even information theory to grapple with the fate of quantum information. No single subfield of physics suffices. Black holes demand integration across disciplines. This unity reflects a deeper truth that nature is fundamentally interconnected, even though we often study it piecemeal for practical reasons. Black holes also connect scales in remarkable ways. Quantum effects at the Planck scale, about 10 to the minus 35 meters, affect black holes that can be millions of kilometers across. Stellar mass black holes formed from individual stars influence galaxy evolution through feedback processes operating over millions of light years. The most massive black holes contain billions of solar masses yet grew from much smaller seeds, possibly through hierarchies of mergers and accretion spanning cosmic history. Events lasting microseconds, the final moments of binary black hole mergers, produce gravitational waves we detect after they've traveled for billions of years across an expanding universe. This interconnectedness across scales and disciplines is part of what makes black holes so fascinating to study. They are not isolated curiosities but nodes in a vast web of physical relationships, touching nearly every aspect of astrophysics and fundamental physics. As our observational capabilities improve, we continue to discover new aspects of black holes. Each new gravitational wave detection adds to our catalog of black hole mergers, refining our understanding of the black hole population's demographics. Each new image from the Event Horizon Telescope or its future enhancements will sharpen our view of event horizon regions, potentially revealing dynamics and structures invisible in single snapshots. Each new X-ray observation or radio survey might reveal previously unknown accreting black holes or catch black holes in outburst states. Future missions like LISA, the space-based gravitational wave detector, will open the low-frequency gravitational wave window, allowing us to observe supermassive black hole mergers and possibly other phenomena not accessible to ground-based detectors. Next-generation radio telescope arrays will achieve even higher resolution, perhaps imaging multiple black hole shadows and studying their environments in unprecedented detail. Improved computational capabilities will enable more realistic simulations of black hole accretion, jet formation, and binary mergers, comparing directly with observations to test physical models. As theoretical understanding advances, new predictions will guide observations, and new observations will constrain or challenge theories, continuing the productive dialogue between theory and observation. There are specific questions we hope to answer. Can we measure black hole spins precisely from accretion disk spectra or gravitational wave signals? Can we detect intermediate mass black holes conclusively and determine how common they are? Can we observe a tidal disruption event in progress and understand the dynamics in detail? Can we detect environmental effects around black holes, such as orbiting clouds or planets? Will we find evidence of new physics beyond general relativity in black hole observations? Can we resolve the information paradox with a testable prediction? When matter falls into a black hole, from an external perspective, it appears to slow down and freeze at the event horizon, never quite crossing, though becoming increasingly redshifted and dim until it fades from view. This perspective might suggest that black holes never truly finish forming, that their event horizons are surrounded by frozen matter from all that has fallen in over their lifetimes. However, this is a result of the external observer's reference frame, where coordinate time to reach the horizon becomes infinite. From the infalling matter's perspective, it crosses in finite proper time and disappears inside. The event horizon itself does not accumulate matter on its surface. Matter crosses through and continues to the interior. This divergence between perspectives is not a contradiction but a feature of how different reference frames relate in general relativity. The external observer's time and the infalling observer's time are not directly comparable once the infalling observer has crossed the horizon. They are in causally disconnected regions. This illustrates how black holes challenge our intuitive notions of time and simultaneity. In everyday experience, we take for granted that everyone agrees on the order of events and can compare clocks directly. Near black holes, these assumptions break down. The flow of time itself becomes observer-dependent in dramatic ways. This has philosophical implications as well as physical ones. It suggests that time is not an absolute background against which events unfold, but a flexible, dynamic aspect of space-time that responds to matter and energy. Black holes take this relativity of time to its logical extreme, creating situations where time for one observer essentially stops from another observer's viewpoint, yet both descriptions are valid within their contexts. The relationship between black holes and their host galaxies has become increasingly recognized as one of the key factors in galaxy evolution. The discovery of tight correlations between black hole mass and galaxy properties suggested deep connections, but understanding the causal relationships and physical mechanisms has required extensive work. Simulations of galaxy formation now routinely include models of black hole growth and feedback, incorporating how energy from accreting black holes affects surrounding gas. These simulations show that without black hole feedback, massive galaxies form too many stars and become too massive compared to observations. The feedback regulates growth by heating or expelling gas, preventing it from cooling and forming stars, or by creating turbulence that disrupts star-forming clouds. Different feedback modes operate at different scales and times. Jets drive powerful mechanical feedback, while radiation from the accretion disk provides radiative feedback. Winds driven from the inner disk or from the outer parts of the accretion flow can carry away gas and energy. These processes are complex and occur on a wide range of scales, from the event horizon to the far reaches of the galaxy and beyond, making them challenging to model accurately. Observations of gas outflows from active galactic nuclei confirm that such feedback occurs, but quantifying its efficiency and understanding its long-term effects requires combining observations with simulations. The interplay between black hole growth and star formation creates a complex coevolutionary history where neither can be understood in isolation. The black hole shapes its galaxy, and the galaxy in turn feeds the black hole, creating feedback loops that ultimately determine the properties of both. This has led to a paradigm shift in galaxy evolution studies, with black holes now recognized as essential components of galaxy models rather than peripheral curiosities. The question of whether black holes are truly black leads us to interesting subtleties. Classical black holes, described by general relativity alone, are perfectly black. They emit nothing. However, quantum mechanics introduces Hawking radiation, making black holes not quite black but rather perfect blackbodies in a thermodynamic sense. A blackbody is an idealized object that absorbs all incident radiation and emits thermal radiation with a specific spectrum determined solely by its temperature. Black holes with Hawking radiation are perfect blackbodies, though with extraordinarily low temperatures for stellar mass and larger black holes. For a solar mass black hole, the Hawking temperature is about 60 nanokelvins, far colder than the cosmic microwave background, which currently has a temperature of about 2.7 Kelvin. This means that at present, such black holes absorb more energy from the universe than they emit, and they glow less brightly than the background. They are indeed darker than empty space. Only much smaller black holes would be warmer than their surroundings and genuinely glow from Hawking radiation. For stellar mass and supermassive black holes, Hawking radiation is a theoretical prediction rather than an observable effect, at least until the far future when the universe has cooled sufficiently. Detecting Hawking radiation directly would be a major achievement, confirming a key prediction that unites quantum mechanics and general relativity. However, the radiation from realistic black holes is so faint that it is swamped by other sources of radiation, particularly in environments with any matter or energy present. Perhaps in very carefully controlled experiments, or through observations of primordial black holes if they exist and are the right size, we might someday detect this radiation. Until then, Hawking radiation remains an elegant theoretical prediction, central to our understanding of black hole thermodynamics and quantum gravity, yet unobserved. The study of black holes benefits from analogs, systems in other contexts that share some mathematical properties with black holes, allowing us to test concepts in more accessible settings. Acoustic black holes, for example, can be created in flowing fluids or gases, where the flow velocity exceeds the speed of sound. Sound waves cannot propagate upstream. The flow sweeps them downstream. This creates an acoustic horizon analogous to an event horizon, where sound cannot escape. Some researchers have used this analogy to explore quantum effects like Hawking radiation in laboratory settings, looking for spontaneous creation of sound waves at the acoustic horizon. While these systems differ in many ways from real black holes, they involve sound rather than light, fluids rather than spacetime, and quantum effects of different fields. The mathematical similarities allow testing of concepts related to horizon physics. Another analog involves light propagation in certain optical media where the refractive index changes in ways that mimic spacetime curvature. These optical analogs can simulate some aspects of black hole light bending and trapping. Studying analogs has value because it allows experimental tests of phenomena that are otherwise purely theoretical when it comes to real black holes. It also provides intuition and insights that can be transferred back to the gravitational context. Of course, analogs have limitations. They cannot capture all aspects of black holes, particularly those involving the full machinery of general relativity and quantum field theory in curved spacetime. But they serve as useful tools for understanding specific aspects and testing whether our theoretical predictions make sense in simpler systems. The existence of analogs across different physical systems also hints at deeper mathematical structures underlying diverse phenomena, a unity that physics often reveals beneath surface diversity. If we consider the life cycle of a single black hole from formation to evaporation, we trace an arc spanning unimaginable time. The black hole forms in a brief moment, the core collapse of a massive star taking less than a second. The newly formed black hole may be surrounded by the debris of the supernova, some of which might fall back and be accreted. Over thousands to millions of years, it may settle into a binary with a companion star or wander alone through the galaxy. If in a binary, episodes of accretion create X-ray emission and possibly jets. The black hole might merge with another black hole if circumstances bring them together. Over billions of years, it may be carried to the center of its galaxy through dynamical friction, joining or becoming the central supermassive black hole through mergers with other black holes. Throughout this time, it grows incrementally through accretion and mergers, but spends long periods in relative quiescence, neither feeding nor radiating significantly. The galaxy itself evolves. Star formation rises and falls. Mergers with other galaxies occur. The large-scale structure of the universe changes as expansion continues. Eventually, after many billions of years, star formation ceases, and the galaxy becomes a stellar graveyard. The black hole remains, now isolated in a dark, cold galaxy in an expanding universe. After tens of billions of years, even close companions have been ejected or consumed. The black hole enters a long period of stillness, lasting for time spans that dwarf all that came before. Slowly, imperceptibly at first, it begins to evaporate through Hawking radiation. The process accelerates as it shrinks. Finally, after 10 to the 67th to 10 to the 100th power years, depending on its mass, it vanishes in a brief flash, returning its remaining mass energy to the universe as radiation. What began as a massive star's dramatic death ends in an even more dramatic but incomparably distant future. The concept of cosmic censorship proposed by Roger Penrose holds that nature prevents singularities from being visible, they are always hidden behind event horizons. This is called the weak cosmic censorship conjecture, and while it is widely believed, it has never been proven rigorously in full generality. If cosmic censorship is violated, naked singularities could exist, regions of infinite curvature not hidden by horizons, visible to the external universe. Such objects would be problematic for physics because they could lead to unpredictable behavior and violations of causality. The laws of physics would break down at the singularity, and the effects could propagate outward, affecting distant regions in ways we cannot predict from initial conditions. Most physicists believe nature avoids this, ensuring singularities always form inside black holes where they cannot affect the external universe. Rotating black holes provide the closest known approach to naked singularities. If spun too rapidly, the mathematics of the Kerr solution suggests the event horizon could disappear, exposing the ring singularity. However, attempts to overspin a black hole by throwing in spinning matter have been shown to be thwarted by various effects, and it is believed that some mechanism always prevents black holes from spinning past the critical rate. Proving or disproving cosmic censorship remains an active area of research in mathematical general relativity. It touches on fundamental questions about the nature of spacetime and whether the universe is predictable. If naked singularities could exist and influence their surroundings, the universe would have regions where determinism breaks down, where we could not predict the future from the present even in principle. The fact that we have not observed any clear evidence of cosmic censorship violation, and that theoretical arguments suggest mechanisms preventing it. In contemplating black holes, we often focus on the physics and mathematics, but it is worth pausing to consider their aesthetic and philosophical dimensions. There is beauty in the concept of a region where the geometry of spacetime has become so extreme that light cannot escape, where time and space exchange roles, where the universe curves back on itself. The mathematical description of black holes, particularly the elegant simplicity of the Schwarzschild and Kerr solutions, has an austere beauty that physicists appreciate. The No-Hair Theorem encapsulates the principle that complexity collapses to simplicity, that from the death of a complex star emerges an object described by just a few numbers. The black hole entropy formula, relating entropy to horizon area through fundamental constants, hints at deep connections between information, gravity, and quantum mechanics. Philosophically, black holes raise questions about the nature of reality, the limits of knowledge, and the boundaries of the universe. They are regions forever beyond our direct observation, separated from us by horizons that light cannot cross. What lies beyond is hidden not by practical limitations of technology, but by the fundamental structure of spacetime itself. This creates an epistemic boundary, a limit to what we can know about the universe based on observations. We can theorize and calculate, but we cannot observe what is inside a black hole from outside. This has echoes of other philosophical questions about the limits of knowledge and the parts of reality that may be forever inaccessible. Yet despite this inaccessibility, black holes are not disconnected from the rest of the universe. They influence their surroundings through gravity. They emit Hawking radiation. They merge and ring, sending out gravitational waves. They are integrated into the cosmos, not separate from it. As we have journeyed through black holes' properties, formation, evolution, and ultimate fate, certain themes recur. One is the interplay between the very large and the very small, how quantum effects at the Planck scale affect objects as large as galaxies, how microscopic physics determines macroscopic properties like temperature and entropy. Another is the unity of physics, how understanding black holes requires integration across relativity, quantum mechanics, thermodynamics, and astrophysics. A third is the role of limits and boundaries, event horizons, singularities, cosmic censorship, the information paradox. black holes are defined by boundaries and push against the limits of our theories. A fourth is the importance of perspective, how different observers see different things, how time flows differently in different places, how there is no single privileged view but rather a web of related perspectives. These themes extend beyond black holes to physics more generally, but black holes bring them into sharp focus. They are natural laboratories for exploring fundamental questions, even though we cannot perform controlled experiments on them directly. The fact that nature produces objects as extreme as black holes, that they exist not as fantasies but as real phenomena in the universe, is itself remarkable. It suggests that the universe explores the full range of possibilities allowed by physics, creating structures at every scale and in every regime where the laws permit. Black holes are extremes, but they are natural extremes, arising inevitably from gravity and the life cycles of stars. They are woven into the fabric of cosmic evolution, from the earliest epochs when the first black holes formed, through the present where they shape galaxies, to the distant future when they will be among the last structures remaining before the final evaporation. They are not anomalies but integral parts of the universe's story. For those hearing about black holes for the first time, or for those revisiting them after years, the concepts can seem overwhelming in their strangeness. Regions where time stops, where space curves infinitely, where quantum mechanics and gravity merge, where objects can evaporate over times longer than the universe's current age. These ideas stretch intuition beyond everyday experience. Yet each concept, when approached patiently, reveals itself to be a logical consequence of principles we can understand. Gravity causes space-time to curve. This is general relativity's central insight. Curve it enough and you create a black hole. Quantum mechanics involves uncertainty and fluctuation. Apply this near a black hole, and Hawking radiation emerges. Thermodynamics relates to counting states and statistical mechanics. Apply this to black holes, and you discover they have temperature and entropy. Each piece builds on others, creating a coherent picture even when the picture describes something as alien as a black hole. The strangeness is real but not arbitrary. It follows from following the mathematics wherever it leads, guided by physical principles and confirmed by observations. In learning about black holes, we are not just learning about exotic objects far away, but about the nature of space, time, matter, and energy in their most extreme forms. We are learning how the universe works at fundamental levels, how seemingly separate concepts connect, how mathematics and reality intertwine. This knowledge enriches our understanding of existence itself, placing us in a cosmos far stranger and more wonderful than our ancestors imagined. Yet a cosmos we can understand through reason, observation, and careful thought. Black holes are destinations in this journey of understanding, milestones marking how far human knowledge has come and signposts pointing toward mysteries we have yet to resolve. We might reflect on what black holes tell us about the universe. They remind us that the cosmos operates by rules that don't depend on human intuition or preference. Gravity collapses stellar cores into black holes regardless of whether we find the result comfortable or comprehensible. Space-time curves according to the distribution of mass and energy, creating phenomena that challenge our everyday experience but follow precise mathematical laws. The universe is not here to be easily understood but to be what it is, and our task is to understand it on its own terms. Black holes teach humility. They set limits on knowledge, hide singularities behind horizons, and operate on scales of time and energy far beyond human scales. Yet they also inspire confidence. Despite their strangeness, we have made sense of them through theory and observation, tracing their properties, detecting them across the universe, and integrating them into our cosmic story. The fact that we, small creatures on a small world, can understand objects as extreme as black hole speaks to the power of scientific inquiry and human curiosity. It suggests that no mystery, however deep, is necessarily beyond our grasp if we pursue it with rigor and imagination. Black holes are natural phenomena, products of the same laws that govern everything else, accessible to understanding through the same methods we apply elsewhere. In this sense, they are not mysterious in the sense of being fundamentally unknowable, but rather in the sense of being complex and requiring sustained effort to understand fully. As we continue to study them, each generation building on previous work, we deepen our comprehension and push the boundaries of knowledge outward. The story of black holes is far from complete. Questions remain, observations are ongoing, theories are being refined, but the progress made over the past century demonstrates that these objects, once purely speculative, are now integral to our understanding of the universe. We have journeyed from stellar collapse through event horizons, encountered singularities and Hawking radiation, observed accretion disks and gravitational waves, explored supermassive black holes in galactic centers, and followed the arc of black holes from birth to evaporation across cosmic time. Each part of this story reveals an aspect of these remarkable objects. Together, they form a picture of black holes as natural consequences of gravity, quantum mechanics, and thermodynamics, acting under extreme conditions. They are regions where the familiar rules of space and time transform into something stranger but still describable by physics. They are objects that influence their surroundings despite their darkness, shaping galaxy evolution and marking the endpoints of stellar life. They are laboratories for testing our most fundamental theories, revealing where our understanding is solid and where new physics awaits discovery. They connect the quantum world to the cosmic scale, the beginning of time to its distant end, the known to the unknown. Black holes stand as monuments to what the universe can create when matter and energy concentrate under gravity's relentless pull. They embody both simplicity and mystery, simple in their description by just a few properties, mysterious in their hidden interiors and unsolved paradoxes. They challenge us to think beyond everyday experience, to embrace mathematics as a guide through territories where intuition fails, to remain open to nature's creativity in producing phenomena stranger than we might have invented. As we conclude this exploration, black holes remain objects of active research and ongoing discovery. Each observation adds detail to our understanding. Each theoretical advance resolves questions or poses new ones. The field is vibrant and evolving, promising future insights we cannot yet anticipate. For now, as we rest and reflect, we can appreciate the journey we have taken through these cosmic extremes. And so we reach the end of our journey through the realm of black holes, from their births in collapsing stellar cores to their eventual evaporation in the unimaginably distant future. Along the way, we have encountered some of the universe's most profound mysteries and most elegant physics. As you rest now, let these ideas settle gently in your mind. There is no need to hold on to every detail. The concepts are there if you wish to return to them. But for now, simply let the wonder of these objects wash over you like a calm tide. Black holes remind us that the universe is vast, ancient, and filled with phenomena that stretch the limits of imagination while remaining grounded in the laws of nature. They connect us to the cosmos in ways both humbling and inspiring, showing us that reality can be stranger and more beautiful than we might have dreamed, yet still accessible to understanding through patient inquiry. As you drift towards sleep, you might imagine those distant points where gravity has carved windows into the fabric of spacetime, where the universe folds in on itself, creating pockets of mystery that will persist long after stars fade and galaxies disperse. But remember too that these are not supernatural or magical. They are natural, emerging from the same physical principles that govern everything else, comprehensible through mathematics and observation. Rest easy knowing that the universe, for all its strangeness, follows consistent rules, that black holes are part of this ordered cosmos, and that human curiosity and reason have allowed us to glimpse their secrets. Sleep well, and may your dreams be as vast and peaceful as the spaces between the stars, as deep as the wells of gravity we have explored, and as gentle as the slow evaporation of a black hole returning its essence to the universe over eons. Good night.